and you in the future, so you can watch it for your physics time. Physics time. It's kind of uncomfortable to look right into the camera, even though I feel like someone's watching. It's probably the total view count will be 0 probably, but. Hello, future Morgan.
Can we all start really close, like all of us get really close?
I would prefer not to have your faces on the camera because of, I don't think it's, I wouldn't say illegal, I think that is just my preference. Because it will be a public YouTube video. You did,
True.
like I said, you signed a waiver saying I could use your likeness for things like this. But like I said,
sign it?
your parents did because you can't because you're a minor. So anyway, like I said, physics time, we're going to talk about torque real quick. So the first thing we're going to do is write down our title, which is torque. Let's include center of gravity into this too. We'll talk briefly about center of gravity, and both of these topics will be on your test. Let's put this symbol here. And torques and center of gravity. The first thing we should do is let's talk about your bell work. Your bell work reads, calculate the torque applied to a wrench that is 20 centimeters long and has a force of 160 newtons applied at its end. Okay? What's the first thing we ought to do?
You have to convert 20
Yep.
centimeters.
Let's convert first. Let's convert 20 centimeters to meters. So the reason for that is that we like to have torque in units Newton meter, right? And if our given is in centimeters, we need to have that in meters so that the units turn out right. So we have 20 centimeters. We're going to convert from centimeters to meters. What should I put on these lines? I think to myself, what?
What are you getting rid of?
What? Okay, yeah, and I already did that part for you. But yeah, what am I getting rid of? Centimeters, so it should be on the opposite side. It was in the numerator, so it should be in the denominator. Centimeters to meters. What should I think to myself about the numbers?
1.
In 1 meter, I think, there are
100.
100 centimeters. 20 divided by 100 is 0.2. The units cancel out, and we're left with meters. Okay? Next step. We could have done this later, but we could have done this after step 1. What is step 1?
Multiply equation.
That's going to be step 2. Step 1 is write down the equation, which is
T,
tau equals,
newtons times meters.
so yes, force times the lever arm. We just put length usually. I mean, that L can stand for lever arm as well. I think the unit, the mechanical universe used was distance, d. I think that's what you had written previously was tau equals fd. This is the same thing, you see, because this is this L for length, the length of the lever arm, right? And when I say lever arm, you know what I mean. Like in this case, a wrench,
Yeah.
you get more what we sometimes call, especially in construction, we call leverage, right? Like if you want to pry open a window, it's almost common sense to us that we would think we'll just get a crowbar or something, right? That allows us to have a longer lever arm. And we'll see why that's important here in a second. So tau, I don't know, but usually I make a little curly hat for it. On this one I did a straight hat. Let's make it curly. Tau equals, in this case the force applied was 160 newtons. The length here, or the length of the lever arm is 0.2 meters. It's really easy when, like in this case, it's perpendicular. The force we apply is going to be perpendicular to the wrench. We'll talk about in a moment here what happens when that's not the case. 160 times 0.2, this is 1/5 of 160, which is what? 32.
Yeah.
Tau equals, so the torque equals 32 Newton meters.
So, okay, I did not convert it, and because I forgot to, but I still got 32,000.
Right.
Like 3,000.
Right, you got 3,200 because it was 100 times bigger than this. Right?
Yeah.
So really what you got was 3,200 Newton centimeters, which is not a customary unit, but it is not wrong. Well, let me say,
Like,
it is
it's
wrong.
not
It's
right.
not untrue, but it is the wrong answer. So let me back up a couple steps here. We're going to draw this picture. I'm going to draw, this is what a wrench looks like to me.
Oh, heck yeah.
That's a pretty good wrench, actually. So this is the little nut. We'll just label it nut.
Dang.
This is the length of the lever arm, right? The lever arm's length is 20 centimeters. And the force applied, where would you apply your force to this to make the nut turn? Let's say we're tightening this nut. Where would we apply the
Right.
force?
To the very end, like.
Yeah, we want it on the very end. That's going to be
But
important.
you're going to be clockwise.
And we're going to want to turn it clockwise. Nope. We're going to want to turn it counterclockwise to make it tighter. So which direction are we going to apply force relative to this diagram? Up. So if I apply my 160 Newton
Up and
force
over.
up, it'll make it turn counterclockwise, which will make this nut tighten, right? And so what is the relation? What's the angle here? Question mark? What angle is this?
90.
Yeah, it has to be what? Perpendicular. The best way for us to apply this would be to make it perpendicular. So if F, which is the force, is perpendicular to the lever arm, torque is simply what? What mathematical operation can we do to make it real simple? What mathematical operation did we do to it?
Multiplication.
Yeah, multiplication. Torque is simply multiplication. Now, you already know the answer to this, or I hope you do at least. What if instead, we're not very good at twisting nuts. Shouldn't have said that. We're not very good at making this tighter, and we instead do it at an angle. Instead of perpendicular, now we've done it at this angle. We'll say this is an angle of, this marker's dying. We'll say this angle is 130 degrees. Can you guess what we're going to have to do with this?
Divide? What did you say? Sorry.
So we have an angle of 130 degrees now, instead of it being perpendicular. We're going to have to do trigonometry. Which component of this are we going to be using?
X.
Try it one more time. The y component. Good, you got it. So which mathematical operation are we going to be doing now? So instead of it being what we had before, it'll now be tau equals 160 newtons times the sine of 130 degrees times 0.2 meters. The units are still going to turn out to be Newton meters. We're just going to have a smaller number. So let's type that in our calculator real quick. So we want to use only the y component, right? In this case. We want to use the component, when I say y component, we want to use the component that is in relation to the lever arm, what direction? We can only use the, yeah, well in this case it's y, but it doesn't, like if the wrench were facing up, it wouldn't be up and down. We would be using the x component. We can only use the component that is what to the lever arm? Perpendicular. Let's write that down on a little side note. Only use the F force that is perpendicular to lever arm. And so in order to find that, we may have to do trigonometry. And the answer to this trigonometry problem was 24.5 Newton meters. So who was the better at tightening this nut? Yeah, this one applies more torque, right? This one applies more torque because it's perpendicular. Whereas this one, same force, right? We have the exact same force, but we applied it at an angle. Can you use this, can you apply this when you're helping Mr. Snitley change the oil in a vehicle? Of course, like this is really, of the physics things we've learned, this might be the most practical, right? You now know if you're trying to tighten or loosen a nut or a screw or something, perpendicular is best, right? Another way, what would be another way we could do this worse? Like
this one?
What do you mean?
Like here's your nut and then
To increase it out.
Okay, yeah, so if we, this is going to be hard to draw, but if this were a real wrench and I grabbed it and twisted it like this,
yeah.
I would get much less what? Torque because my what is smaller. I might even be applying the same force still, but my what is smaller now. Lever arm. So another way I could do it bad is this would be the correct way to hold the wrench.
Like
but if I choke up on
driver,
it, the torque is going to be lower because my lever arm is lower. So conversely, if I have a real stuck nut, right? What would be a good way to get it unstuck?
Like
The distance.
Increase the distance. How? I can't make my wrench longer.
Move your hand farther down the arm.
What if it's already as far as it can go?
Bigger one.
Yep. Longer wrench, which is generally why you see someone's wall in the shop, and these are not going to be as good a wrench, but they're kind of like this, right? The bigger the diameter of the wrench gets, also the longer it gets. Because usually, for a larger nut, we need a longer wrench to get it stuck or to tighten it or loosen it, right? These are not good drawings of wrenches like this one was, but
They look like people.
But I think probably your dad in his shop has a wall of wrenches, and I think if I remember correctly, it's engraved steel, like it's a piece of metal that has been cut out to say like here's the 3/8 inch wrenches, here's the 1/2 inch wrenches, and you can see the smaller the diameter. Yeah, that's what I mean.
Yeah.
The smaller the diameter is, the shorter the wrench, because generally we need less torque to loosen or tighten that size of nut. Anyway, so there's another thing that if I have this nut and I want to, if it's really, really stuck, what could I use? Can't make the wrench any longer because I can't use a larger size wrench because the nut is a certain size. What could I do? You've done it before, maybe. I've done it before.
Say it again?
What can I do to make this is stuck, right? No matter how...
Add on a stick?
Yeah, exactly. Add on a stick. You wouldn't like duct tape an actual wooden stick at the end, but you could use something that I've heard my grandpa always calls this a cheat bar. It's a pipe that you slide over the end of this to make it the lever arm longer, right? So you get a 6 foot long, we don't use feet, you get a 2 meter long cheat bar, and it's going to make the lever arm, instead of 20 centimeters, now it's 200 centimeters, right? That multiplies the torque by 10. Do you see why this is, like, this, by using physics, we can really make things a lot easier or more difficult for ourselves. Look at, I've experienced this door in real life, not this exact door, but there's a picture of a door on page 151, and I'm going to draw it so that people without their book can see it, and it looks like this, and it's a cool looking door. It's got, like, the doorknob's right there in the middle. Mm-hmm. It's cool looking. So from a design standpoint, is this a good design for a door? Yeah, it's cool looking. But from a physics standpoint, is this a good design for it? But
you're going to have to open it like...
Right, because the lever arm here, I don't know where the hinges are, we'll say the hinges are here. The lever arm, for when we turn it, is only
the window above, it makes it look better.
Yeah, you're right. The lever arm is shorter than it would be for a normal door, right? And so this is from a physics standpoint, like I said, this is a cool looking door. Truly, if I was going to change the door of my house, which I probably will someday, this is a front runner. I think this is a sweet looking door. But from a physics standpoint, it's not an efficient door. But you know what, doors are not really that hard to open. Like if the hardest problem in your life is that it's too hard to open your front door, you might have a really easy life. So I think this is cool. I think the design coolness of it outweighs the
hardness,
the difficulty of having this door.
I think that you should put 2 doorknobs, like one in the normal spot, one in the middle,
one over here.
So then
you can
grab in the other one.
You can test who knows their physics better. And like I said, a lot of this is just like, it feels like common sense. Like it's second nature that if I want to get a better, more torque on my wrench, I either slide further down the handle or I start moving it at a perpendicular angle as opposed to some cockeyed angle, right? The torque, we've done all the math. We really have to kind of do this backward because let's define torque real quick. I'm going to use my fancy T. Torque is what?
Like his turning object, a rotating object.
Yeah, torque is, I'm not going to use the word force, but torque is a way to cause, let's put a change in rotational momentum, right? In the same way that force, well, a lot of times we relate force and torque. In the same way that force, Newton defined it as a change in momentum, which is true. We've talked about this previously. Newton defined force as a change in momentum. We could define torque as a change in rotational momentum, right? And in the exact same way that Newton's third law tells us that if I change the momentum of a basketball, say, that basketball changes the momentum on me exactly the same amount, right? For every action, there's an equal and opposite reaction. Same thing with this. Any torque that's applies a reverse torque back, right? So if I want my podium, can you see it on the video? Come on, podium. If I want my podium to rotate this way, I have to rotate my arms the other way, right? Like I said, this again is almost counterintuitive to us. Not counterintuitive. This is almost like so intuitive that it makes it's unreasonable to talk about it. But like if I want this to rotate clockwise, I need to rotate my hands in that way as well, right? Because if I apply a torque, this applies a torque back to me. Torques don't come from nowhere. We have to have action and reaction, just like forces. So torque is a way to cause a change in rotational momentum. And there's several ways that we can calculate torque. One, the one that I kind of like the best, in the same way we had F equals ma, you remember F equals ma, I hope, right? The same way we had F equals ma, we can calculate torque in this way. Torque equals the moment of inertia, which is I, times the angular acceleration. I'm trying to use the same. I've always called angular acceleration alpha, but I won't use the same phraseology as your book. Can't really find it, so I'm just going to write it alpha. So we already had a formula for torque. Torque equals force times lever arm, which is fine. But here's another one that's a little bit, I think, more fundamental. Torque, where T is torque, not T, I'm sorry, tau is torque, measured in Newton meters. I is moment of inertia. And we'll talk about that in a second. But moment of inertia is measured in kilogram meters squared. And A is angular acceleration, which is measured in theta. We could put theta, radians. Remember, radian is kind of like a unit that we don't, like it drops itself out. Radian per second squared, right? Because acceleration is seconds per second. Like when we had linear acceleration, it was meters per second, right? The acceleration of gravity was 9.8 meters per second, which we also called meters per second squared. In the same way, angular acceleration is radians per second squared. It's not how fast the thing is rotating, it's how fast the rotation is changing. With me? Mm-hmm. And look, these units, like I said, the radians kind of don't, that's like a pseudo unit. So the units come out to be kilogram meters squared per second squared, which we know is a kilogram times meter per second squared, not meter squared, is a Newton. And we have a square meter, so it's just Newton times meter. Look, this unit ends up being the same as that, obviously. So this, like I said, this is, I would consider the most fundamental way to measure torque. We don't really use this one very much because this is a hard thing to measure. And this is a hard thing to calculate. It is measurable, but it's kind of a difficult thing to calculate, and we'll talk about why in a second. This one is much more useful, and really, frankly, quite a lot easier. But this one's more fundamental, and see how it lines up really neatly with F equals ma, because in the same way that a force causes a change in linear acceleration, a torque causes a change in angular acceleration. And so we have those things here, and then moment of inertia is like mass. Let's talk about moment of inertia first. I guess we've already talked about angular acceleration. Let's talk about moment of inertia. In your book, there's a picture I really like on page 155, and it has, I'm going to draw on the board again for whoever doesn't have their book. This is supposed to be, you might think, wow, that's a nice fork. This is not a fork. It's supposed to be a hand. Imagine you have two different dumbbells, right? In both cases, the dumbbell is going to weigh, we'll say 10 kilograms, which is roughly 25 pounds. It's 22 pounds, but you know what a 25 kilogram dumbbell feels like, right? I've seen all of you lift weights. So in both cases, the dumbbell weighs 10 kilograms. I'm sorry, it has a mass of 10 kilograms. And the first one, the dumbbell is situated like this. Remember, both of them have the same mass. And we're going to say they both all together have the same length, but they're arranged differently, right? Which one would be harder to spin?
The one with the at the end.
Yeah, this one is harder to spin, right? Why? They have the same mass. Going back to this, what's different about the second one? The lever arm. And this is what we call, this whole principle is called moment of inertia. It's the difficulty in rotating an object. In the same way that inertia, regular inertia, was the difficulty in changing an object's linear motion, moment of inertia is the difficulty in changing its rotation inertia. Okay? So think about it like that. And now look with me, we're not going to, you don't have to memorize these, but look with me on page 157. These are all the different formulas, well no, not all. These are some of the different formulas for rotational inertia. This won't be on your test, but if you're watching this, like when you, man, I hope this is useful to you when you go to college, but if you want to watch this video again when you're at college next year and you're taking university physics, you can go back to this because I'll just say it and you can pause it when we talk about it. But for a simple pendulum, look, the formula for moment of inertia, I, for a simple pendulum is I equals mr squared. I is what, of course? Moment of inertia. M is mass, and r is radius. So we basically multiply the mass of the pendulum times how far away it is from its swing point and square that. For a hoop, it's also I equals mr squared. For a hoop about its diameter, that means spinning on the other axis, it's I equals 1/2 mr squared. Look at all the rest of them. Do you see how all of them have this mr squared? They're all going to end up being kilograms times meters squared as units, but some of them have a coefficient at the front. For instance, the hoop was 1/2 mr squared, the cylinder is 2/3 mr squared, the stick about an end is 1/3 it has L because it's the length of the stick, but mr squared basically, right? So all the units end up being the same, they just have different factors that they're changing by. And which ones have the largest factor? What is the largest coefficient out of any of those?
2/5.
No?
Is it just mr squared?
Yeah, it's no coefficient, right? It's just one. One is the largest out of any of them. And that's the hoop or the pendulum. And that's because in this, look at this. This would be like either the hoop or the pendulum because the mass is as far away on the lever arm as it can possibly get. And look, the ones that are smaller have more of the mass closer to the center. You see that? So like the sphere is 2/3 mr squared because more of the mass, certainly not all of the mass, but more of the mass is closer to the center. The stick, the same way. More of the mass is closer to the center. So the moment of inertia depends on the mass of the object, right? We'd have a greater moment, we'd have a harder time rotating it if it was a 100-pound dumbbell than if it was a 20-pound one. And also depends on how far away it is. We have an easier time rotating the one with the mass concentrated closer to our axis, right? There's one other way. I'm going to erase some of this stuff. So far we have two ways of calculating torque. The kind of nice, useful, practical way with force times lever arm. And then we have the more theoretical way, which you will sometimes still use, and you should definitely have it written down. But this way relates it to F equals ma a little bit better. And then the third way, this is the way, I don't know for sure that Newton ever talked about torque, but this is the way Newton would have described torque. So to Newton, torque would have been change in L over T. He invented the calculus, and so he would have written torque equals dl over dt, but that means the same thing to us algebraically as delta L over T. So in this case, T is torque still, measured in, can you guess? It's still going to be Newton meters. L, well, delta L, is change in, we call this angular momentum. And this is measured in kilogram meters squared per second. Which is, I don't know, borderline meaningless unit. It just, obviously it depends on its mass, it depends on its axis, the length of its axis, how far away it is from, like this, how far away the mass is from the center, and then it depends on the time that it's spinning, like how fast it's spinning. And then T, of course, is really easy, time measured in seconds. And once again, these units end up being Newton meters, just like they did down here, and just like they did with force times lever arm. But this relates to the equation for force, which is F equals delta P over T, which is force equals change in momentum over time. This is how Newton described linear force. And so, like I said, this is how Newton would have, or possibly did, describe torque. It's the same exact thing, except for instead of linear momentum, it's angular momentum. Do you see the parallels? So we started out in chapter 9 by talking about linear velocity versus angular velocity and what the differences between those things are. And then chapter 10 and chapter 11 are all about linear force versus angular torque, right? There are parallels. So remember Dr. David L. Goodstein saying on the video that there are three fundamental properties of the universe, right? Three fundamental conservation laws. Do you remember what they were? The law of conservation of
mass,
which we include in energy. So law of conservation of energy, law of conservation of momentum, and law of conservation of angular momentum, right? And so those last two are what we've been talking about basically all year. We're talking about how movement is conserved. Right? We did talk a little bit about energy, but how movement is conserved, both linear movement, momentum, and rotational movement, angular momentum. Do you have questions about any of this? We do have a couple other things I want to talk to you about, but we're going to do a demonstration which will be difficult to show on camera. But do you have questions about any of this to begin with? let's try to do the demonstration on camera because I think it's interesting, so stand by. Okay, welcome back. We have this little thing set up here. So what's going to happen is Haley is going to hold out the gallons of water at an arm's length. You don't have to do it right this second, but she's going to not drop them because it'll make a mess. She's going to hold it out at arm's length, and then Kaylin's going to spin her as fast as she can, and then Haley is going to bring those in. So listen, as we do that, as Haley brings the gallons in, what's going to decrease?
The speed.
Well,
Increase the
right.
speed.
So the lever arm will decrease, but the angular momentum must stay the same, right? And angular momentum depends on the masses, how far away they are, and how fast she's spinning. So is the mass going to change? No. And how far away they are, is that going to change? Yeah. So if it gets closer and the angular momentum must stay the same, what's going to happen to her speed? It's going to go faster. So what we should see, and you'll see this in ballerinas too if you ever watch ballerinas, what you should see is that as she brings them in, she's going to speed way up. So
Like when you spin on a tire swing and then you take it.
exactly. So let's try it out.
Fast. These legs aren't going to stop.
Yeah, you like have to spin her by her arm.
No.
Did you notice it go faster?
Yeah, I went faster.
Okay, someone else want to try?
Oh. I can hold the. It hurts to turn. These are trying to measure. That's as far as I can go. Yes.
Spin her by her arms. Yeah, look at that. You want to try Morgan? Yes, you do. Come on.
I don't do very good with
Well, if you need to throw it in the trash can over there. Hand her weights,
Or hold them out all the way.
if you can. Spin her by your arm, really fast, as fast as you can. And then wait, keep going, faster, and then pull them in, Morgan. You want to try it again, Haley? That's kind of fun, right? So like I said, what happened
It
is
made me dizzy.
the angular momentum depends on, as we can see from the units. Oh, we can't because, hold on. Pause there. Okay, so as we can see from the units of angular momentum, it depends on the mass of the things involved. Meters squared because it depends on the distance away from the center of mass that the masses are, and meters per second because it depends on how fast their linear velocity, right? So when we had a certain mass, the mass didn't change, and we made the lever arm shorter, right? We decreased one of these meters, which made the speed increase because L itself, angular momentum, can't change, right? So L1 must equal L2, and if L1 has a high lever arm, then L2 must have a high velocity, which was why you speed up the closer those things get. And you'll see a ballerina do this when she spinning, and then she'll go woo like that, and then she'll spin a lot faster.
Like a figure skater.
I mean figure skater. I don't know. I can't tell the difference between ballerinas and figure skaters. All right, bye.